In this video, we will see stress distribution in torsion load. So here, the first case is solid shaft. So if we applied torque in solid shaft, then if we see the cross section, this is the cross section of the solid shaft. Shear stress is zero at the center, and due to the rotation of all the layers, so imagine like a ring formulation of each and every layer up to this point. So each and every circular fiber will have different stress from 0 to the maximum. So at the end there will be maximum, which is equal to tr by j, which we have seen in torsion equation. So this is for solid shaft. Now here if you see, torque at particular distance from the center means at particular radius, torque at r will be equal to tau maximum divided by capital R into small r. So the ratio tau upon r will be constant, which will be equal to t by j. J is a polar moment of inertia, where j is equal to pi divided by 32 d raised to 4. So torque at r upon r equal to tau max upon capital R. Capital R is the maximum radius, and which is equal to torque applied divided by j. D is the diameter of this shaft. So this is how linear relationship is followed with respect to R. So shear stress is distributed like this, increasing from 0 to maximum with 0 to capital R. In hollow shaft, the same distribution follow, but here on this hollow section, this is the hollow region. So here there is no shear stress, and there is a minimum shear stress which is on the inner radius till the maximum value. Here only this J value changes, which is equal to pi by 32 d naught raised to 4 minus di raised to 4. So this is how distribution is in hollow shaft, where here in this triangle there is no shear stress. Outside that there is this distribution of shear stress from this tau minimum to tau maximum. Now we will see compound shafts. So here if you see shaft in series, so there if there are two shafts with different diameters or materials, and there is a one torque applied at T1. So now here torque throughout this shaft will be equal tau 1 in this also will be equal to tau 2 in this bar will be equal to tau which is applied, and the theta angle twist at the end theta, which will be equal to theta 1 of this particular shaft 1 plus theta 2 of this particular shaft theta 2. So theta 1 will be different, theta 2 will be different, but the combine, if we add it, we will get theta at the end, and theta 1 will be equal to t1 l1 by g1 j1 plus t2 l2 by g2 j2 will be theta 2. So here torque is same in both the cases, length can be same or different, g1 is material can be same or different, and j is different because diameters are different. Now there are many cases like one torque t1 is applied here, t2 is applied here. So in that case, if t2 is applied here, some other or other torque is applied here, let's say t dash. So in particular one shaft there will be t plus t1 both, and on 2 there is only t, because if we ignore this there is only t on here. If we draw free body diagram, opposite will be acting on the other end. Now this t is transferred to this, and we are applying t dash, so both will be acting on one. So that is how we have to analyze the different cases. So here we are not applying this t dash. Now if shafts are in parallel, means if you see circular shaft 1 and outer ring hollow shaft 2, both are sticked together. Now if we apply torque at one end, then this torque is distributed in 1 and 2 differently, because both are resisting the same torque. So T will be equal to T1 plus T2. So T1 will be acting on the inner shaft, T2 will be acting on hollow shaft. So both are taking different loads, and the angle of twist at the end will be same because both are sticked together. So angle of twist will be same for both, theta will be same for both, and theta 1 will be t1 l1 by g1 j1, and theta 2 will be equal to t2 l2 by g2 j2. Here length is same, and j and g can be different, t1 T1 and T2 are different. So this is how you have to get those equation and solve problems of shaft. And thank you for watching this video, and see you in the next video.